Epilepsy. Epilepsy is a common condition that affects the brain and causes multiple unpredicted seizures. People with epilepsy cannot live a normal life. 65 million people globally are affected by epilepsy, according to Healthline, and 1 in 26 may develop epilepsy anytime in their lives. This project was inspired by the cousin of one of the team members who had epilepsy since he was born. He couldn't accomplish any human need. He couldn't cook, he couldn't live alone, he couldn't have a career, and he couldn't even sleep. That's why the team member had this idea to help patients with epilepsy to live normally. This project uses deep learning and IoT to predict the seizure half an hour before it occurs. It then sends an alert to the relatives or the hospitals. Also, it monitors the driver's state constantly to avoid accidents due to distraction. If the distraction is detected, then an alert will be sent to the surrounding cars and the car can park automatically. The monitoring of the brain is used by Muse2 to monitor the EEG. The pre-processing is done by the Raspberry Pi. The codes are done by the deep learning. Any medical information is based on the help of the medical experts.
Our project is mainly depend on taking EEG signals from the patient's brain through using Muse2 headset. So, what is EEG? EEG is a prefix of electroencephalogram and it is a recording of a brain activity. The main frequencies of human EEG waves are alpha, beta, theta, delta. Alpha has a frequency between 7.5 and 13 Hz. It appears when closing the eyes and relaxing, and disappears when opening the eyes or alerting by any mechanism, thinking, calculating, etc. It is a major rhythm seen in normal relaxed adults. Beta is fast activity. It has a frequency of 14 and greater hertz. It is usually seen when both sides in symmetrical distribution and it is most evident frontally. It is a dominant rhythm in patients who are alert or have their eyes open. Theta has a frequency of 3.5 to 7.5 Hz and it is classified as slow activity. It is perfectly normal in children up to 13 years and in sleep adults, but abnormal in awake adults. And delta has a frequency of 3 Hz or below. It tends to be the highest in amplitude and the lowest waves. It is normal as dominant rhythm in infants up to 1 year and in stage 3 and 4 of sleep.
What is the impact of epilepsy? Can having seizures make me more likely to develop other problems? Okay, some health problems are seen more often in people with seizures than in people without seizures. They could be related to the seizures or they could be due to whatever is causing the epilepsy. For example, mood problems or changes could be related to times of seizures or side effects of medicines. Yet, mood problems may also be a separate problem. Some related conditions may include not doing well at home, school, work, or with friends, unexplained injuries, falls, or other illness, reproductive problems, risk of death. We benefit from this information about seizure in seizure prediction and detection part in our project.
Seizure prediction. Seizure prediction was used using the deep learning. First, we made the pre-processing to convert the EDF files into a spectrogram. Spectrogram is a graph that uses frequency over time so that we can detect the frequency components. Actually, each frequency component defines the state of the brain. Then the training is done on a 3D convolutional neural network consisting of a 3-layer. But actually, the data set which was used, which is CHB-MIT, was really simple for the depth of this network. That's why overfitting occurs. Another data set was used, which is the American Society for Epilepsy. And another code was used, which consists of a convolutional 2D network. With changing some parameters, the accuracy reached 96%, which overperformed the accuracy proposed in the paper, which was 86%. So now I'm going to talk about the embedded systems and the cloud of this project. This is the system flowchart. So basically we start by the data acquisition, then the data is sent to the Raspberry Pi, then we feed the AI models this data. In case the model of the seizure prediction predicted the seizure, the application will alert the user if he responded. Then we go back to the data acquisition if he didn't respond. Then the Park Assist and cloud protocols are triggered. In case the model of the seizure detection detected a seizure, the Park Assist and cloud protocols are triggered. In case the fatigue detection model detected that the user is drowsy, we alert the user through the application if he didn't respond in a very tight time frame. The cloud and Park Assist protocols are triggered. This is the data acquisition block. So we have the Muse 2 headset, the heart rate, and the temperature sensor, and of course the accelerometer. This is a video of the heart rate. This is a video of the output of the Muse 2. And this is a video of the output of the GPS module.
In this method, the paper uses this technical approach, which include, firstly, transform the input EEG signal from the temporal space to the information space by calculating differential entropy, which can also reduce the dimensionality of high-dimensional data. Then, find local patterns from the transformed EEG that can be related to the temporal analysis, and find the global and spatial relations. Overall, the network follows the conventional steps of feature representation and classifier learning. Therefore, the proposed method can be analyzed and understood according to the mainstream in EEG decoding. On the other hand, the major difference of this method over the other method is that we exploit both benefits of linear model-based machine learning, deep learning, and hierarchical learning approaches. We use the feed-vec dataset and applied deep learning on it by the following process. First, signal acquisition. Second, pre-processing of the data. Third, feature extraction using differential entropy. Fourth, classifications. And finally, to the BCI application to determine the condition of our patient. We used publicly available feed-vec dataset. It consists of 23 trials, and each trial has about 2 hours EEG signals. These samples are acquired from 17 electrode channels according to the international standards system and sampled from 200 Hz. This dataset is labeled by Berkool levels, so we categorize the labels value of 3 classes, awake, tired, and drowsy, by setting 2 thresholds, 0.35 and 0.7, for the classification experiment. We are presenting a solution to the world to help those with epilepsy condition to have the ability to act like normal people, to drive a car, to feel safe, to be alone anywhere, because they have trust in our system that it will provide them with the immediate help and warn them whenever they are having a seizure within 30 minutes. We are developing an integrated software to predict epileptic seizure period occurrence and detect our client fatigue and focus while driving their cars. Our system consists of a wearable headset with a portable device easy to carry in your pocket, and you are ready to go.